Okay, so what I'd like to give is an idea of our overall approach, a framework for how we get to median motions, and in particular, a set of median motions that will be used in the logic tree. And I have a number of slides and ideas that Norm has gone over, and so I'll go more quickly over those to save time and spend more time on the framework ideas. There we go. Okay, so for Palo Verde, what we have done is to verify published GMPs against nearby records for distant California earthquakes. This is work that Jenny Watson-Lamprey did. Norm showed a number of examples for that. Other thing that we've done is to look at or assess path differences in Q for sources that are coming from the west, the large magnitude California earthquakes. And we've investigated whether what we are going to do is, as Norm pointed out, we're going to investigate whether there is a regional source effect. And he mentioned the possibility of low stress parameter events in the Salton Trough, for example, as an example. So some of the same slides that Norm showed, I guess I'd just reiterate the point that the comparisons of the Arizona data with the NGA West 2 data as well as the GMPEs are consistent, and so it does not appear that there's a need for a regional Q adjustment as proposed by Watson-Lamprey. Wrong down arrow. Okay, so one of the other things that we're going to be doing, and this is really getting to the framework of the approach, is to use a method that maps that's basically a high-dimensional visualization method that Scherbaum's developed with Nico Kuhn. After lunch, Nico's will be giving an in-depth overview of the method, so you'll have ample opportunity to become more familiar with it. Of course, we've already seen examples in Workshop 2 and Workshop 1. For Palo Verde, the way that it would be implemented is to use the high-dimensional visualization method to compare the NGA West 2 GMPs with perhaps GMPs that have incorporated normal type earthquakes. For example, the European data sets, Akar and Bindi could be an example, or with other normal event data such as the, not Little Skull Mountain, but the Wells earthquake. Okay, and in the interest of saving time, I'm going to be introducing this idea for the large strike slip case at Diablo Canyon. So let's look at what we've done for Diablo Canyon. Well, we've evaluated the published GMPs for relevance, the type of earthquakes that went into building the GMPEs, the extent of the data, or the distances at which those observations were made, whether or not they incorporate hanging wall effects or use RJB. At Diablo Canyon, the site is everywhere on the hanging wall for the dipping reverse faults. We've also evaluated rules for accounting for complex and splay rupture scenarios. This is the last ideas that Norm was presenting, looking at the how do we combine motions from the GMPEs in a manner that would be the most consistent for these more complicated cases. Evaluate approaches for accounting for directivity terms to be applied to the base GMP relations. This is work that Jenny Watson-Lamprey has been working on and will be presenting later at the meeting. We're in the process of evaluating magnitude scaling of hanging wall terms for the small magnitude events. This is based on the numerical simulations. And as Norm pointed out, it would be looking at adjustments to the magnitude scaling terms in the published relationships. There's also possible path adjustments for onshore versus offshore sources. And really, the bulk of the work is using this high-dimensional visualization approach that I will describe in the next few slides to investigate the correlation space of the selected GMP models and to use correlations between the GMPEs, independent data and numerical ground motion simulations to develop a distribution of new ground motion models that can help by both interpolating and extrapolating between published GMPEs and extrapolating beyond those published GMPEs. And what we'd like to do is to use information in this context to inform and assign logic tree weights.
Before you go on, I expect we'll get comments, but independent data is probably not the right word there. The data that we're going to be showing are dependent in that many of them were used to derive the GMPEs. So we don't have an independent data set to use as testing, but we'll do...
But subsets of the
right,
data.
Right.
Yeah. Okay, so this is the basic idea. So on the left hand, we start with candidate GMPEs. Our discussion centered around how appropriate different models might be, additional data sets that they bring to the overall characterization. So we may start with a set of 6 or 7 GMPEs that can be captured with a common form. And this is an important point, because what is done practically is to take these individual GMPEs and then produce a synthetic data set of ground motion values for particular magnitude ranges or discrete magnitudes, distance ranges, and period. And then those simulated data from the GMPEs are fit to this common functional form that's carried forward. What this enables is it develops a vector between the fitting coefficients to this synthetic data set from the GMPEs. So this is an example from Scherbaum's paper in 2010 that shows for a number of GMPEs the correlation matrix for these. And the point is that given the range of discrete magnitudes, the range of distances and periods, that this results in a very high dimensional vector space. And what Scherbaum has shown is that there are techniques in which you can map from the high dimensional space to a lower dimensional space, and in particular, a two-dimensional space. And the actual numerical computation is done so that the correlation structures for the high dimensional space and the two-dimensional space are equivalent. The advantage in this is that you can then map the projection of these vectors in a variety of ways, and Nico Kuhn in Workshop 2 described 3 of them. And what's shown here is one, the Salmon's map. And in the most basic sense, what you can do with this is just look at the distance between the projections of these models in this space and assess how similar or dissimilar the models are. So for example, this cluster of models here, they're very close. They are more similar in characteristics than, say, a comparison between, there's the arrow, this one and perhaps this one. It's further away. So the question is that there's a lot of space in these models, and then there's clusters, and what about the outer reaches of this? So what you can do then is, with the correlation structure, you can randomly sample the fit parameters and then develop a sample set of maybe perhaps 1,000 new models, new GMPE models. And you can plot this in the Salmon space. So what this is showing now is the original GMPEs, the 7 GMPEs, and their projections into the space, and then through this process, 1,000 realizations of the joint parameter distribution. Okay, so each one of these points can be thought of as a new GMPE. And maybe an easier way to think about this is when you're looking at the magnitude scaling, for example, at a distance of RJB equals 15 kilometers, then what we have is a distribution of these GMPEs, and plotted for reference are the 7 GMPEs that went in to develop this correlation structure between the models. Okay, so what you can see is that these models are within the distribution, and that the gray curves are providing some information about the tails of that distribution. This is for magnitude scaling. You can look at the same sort of plot for distance scaling. This is for a magnitude 6.5 earthquake. Oops. And again, you know, similar behavior. So one of the things that we look at here, for example, is we see what is argued to be more or less a common functional form for the distance attenuation. You can see that some of these GMPEs are getting flatter. So one aspect of this is what is the appropriate range to analyze within the Salmon's map, and potentially there are models that would deviate significantly from our experience in observation. Okay, so what we have now are these 1,000 new models, and the next step in this is to try to characterize the likelihood of given models and plot this in this space. The way this is done is to select subsets of data, worldwide earthquakes for magnitudes greater than 6.3, for example, worldwide greater than 5.5. For each of the 1,000 sampled GMPEs, you can compute the likelihood of these models and then plot it. And what Nico's going to show later, one of the very clear advantages of this approach is that not only can you look at the relationships between the input or candidate GMPEs that are used to construct the correlation structure, but you can also relate it to the sample models. You can think about it in terms of the mean of the parameter distribution, which is this black circle here. And you can also plot finite fault simulations and maybe other data sets that are in addition to what, for example, other data sets that may not have been in the NGA West 2 data set. So you're really starting to be able to look at the different contributions from these different data. All right, so the next step then is, well, how do you interpret this? And there'll be a lot of discussion later about where to center this and how to sample this region and essentially divide it down into subregions into a manageable number of GMPEs to be used in the hazard analysis. The working model now is that this model space would be subdivided into perhaps 10 subregions, and within each subregion, and this is an illustration that shows this, within each subregion there would be a representative GMPE that would be carried forward. Okay, so the questions are, how do the simulations and additional ground motion data sets compare to the model distribution on the GMPEs? Is this the appropriate point to center, or is there other information that can inform on that? How do we treat the tails in this distribution? These are things that we're thinking about. Okay, so once you've done that, then you've developed a base model now, a base model of 10 GMPEs. What I neglected to say at the beginning is, and let me scoot back just to the plot because I think it will be a little bit clearer, and there's a few other points that I wanted to make, is that these are the GMPEs that we settled on because they could be fit by a common functional form. Also, this is for the large magnitude strike slip sources for Diablo Canyon. So the candidate GMPEs that will go into this process at the beginning will be different for the reverse source cases. And at Palo Verdes, they'll be different in that models like, so for example, for the reverse case, Idris model and the Zhao models would not be used, but other models like those models would not be used. For the Palo Verde case, these models would not be used, but perhaps Akar and Bindi could be brought in because those models are taking into account contributions from strike-slip sources. The other thing that we can do is if there are models that are bringing information to the problem that are not able to be captured by this common functional form, which is a requirement of the approach, that they could be brought along as separate base models. And so that's what this diagram is showing. Here we have our set of 10 vector models, and then the Graves, not the Graves, the Grazer and Kalkin 2013 GMPE could be brought along as an additional model simply because it cannot be fit by the same functional form. There's additional information that's brought forward in their model. So if you have distributions of these points within the subregions and the estimations of likelihood, that could be used to assign in a somewhat objective way the weights for each of these models that are going into the logic tree. There are also weights for alternative data sets that should be considered. And so alternative data sets, and I think Bob will be talking more about this tomorrow when he's presenting the logic tree. There's data sets for the magnitude larger than 6.5, larger than 5. For Palo Verdes, it would be the NGA West 2 models, also consideration of the European models. Okay, so this is the approach to get to the base median models. And the next thing that needs to be done are the adjustments to these models. I'm not going to say very much in detail about any of these except just to point them out. So one would be directivity corrections that the groups looked at, and Jenny Watson-Lamprey will be presenting her model later on at this meeting. The other is display faults and complex faults, and coming up with a rule. As Norm pointed out, there are 4 rules that were considered. It looks like the SSRS is working quite well to capture the behavior for these complex cases and display cases. What about hanging walls? Well, for Diablo Canyon, since all of the sites are on the hanging wall, we'll be using a hanging wall-based model. For Palo Verde, there'll be random virtual sources in the home region of the model, in which cases there would be footwall and hanging wall terms applied in the hazard calculation. In terms of so I said that. Okay, so the first bullet is that one of the things that we've done that we're actually in the process of doing now is to use the simulations to look at the magnitude scaling adjustments that need to be made to existing GMPEs for the magnitude 5.5 and magnitude 6 simulations, and relating them into the larger simulations that were used in the earlier work. And finally, there are path adjustments. And for Diablo Canyon, there'll be work discussed later at the meeting and plans for looking at onshore, offshore differences in the paths. So to summarize, the considerations for median motions has been to evaluate published GMPs for relevance to study areas, the types of sources that go into the construction of those relationships, the extent of the data, incorporation of hanging wall, or use of RJB in the case of Diablo Canyon, where we have dipping fault cases to consider, and the test of these relationships with additional ground motion data sets, some of the work that Jenny showed for Palo Verde. We're evaluating rules for accounting for complex display rupture scenarios to be applied to the GMPEs in the hazard calculations, and evaluating approaches for accounting for directivity, which will be discussed later in detail, the approaches for hanging wall terms to be applied for the base GMPE relations, and then the path adjustments that we'll be talking about a little bit more. But the heart of the approach is the use of this high-dimensional visualization method to identify correlations between the published GMPEs, alternative data sets, or subsets of data sets, the numerical simulations, to develop a broader sampling of possible GMPE space or GMPE relations, interpolation and extrapolation, and then to use this information to assign the logic tree weights. And that's the last slide. And we have a few minutes.
Okay. Questions for Doug? Do you know what we're doing? And Ralph says no. So go ahead, Steve.
This is just a question for clarification.
Put it closer to your.
Can you hear me now?
Better.
Good. Boy, it's got to be close. All right. Swallow the thing. All right. After you have done the salmon map and partitioned it as you showed, is the idea here, and you used the term representative GMPE, if there's an existing GMPE inside one of those partitions, is the intent to use that as the representative one, or in all cases are you going to generate some kind of a centroid GMPE, or have you not gotten that far yet?
Well, I think we've been thinking about those. I think we've been thinking about that as alternative approaches. So one would be to use a representative GMPE within that region. Another approach could be also to have, say, the 10 regions that are constructed from that distribution, and then also bring forward the candidate GMPEs themselves. That would be another possibility.
Yeah, so we really are not set. I think what we will do is pick a centered model within each region, which would be not a published GMPE in general. And also, if there's a GMPE in that region, we want to run the hazard for that one, and for our own understanding, are those numbers significantly different or not. What you'll see later today, or when we're going through these, when we have reparameterized the GMPE with the common form, the hazard is very similar. So that part is not fundamentally changing it. But there are advantages to using the published GMPE in the zone as opposed to replacing it, because they do have additional complexities that we haven't been capturing. So that's part of what we're working through, and I'm sure on the first pass, we'll run it both ways.
You'll always have that kind of a reality check.
Yes, we need to make sure we're not missing something or losing something fundamental when we have gone to this common form. Ralph.
So Doug, when you were showing the, let's say, the GMPEs in red, and then you showed basically a large suite of these other alternatives, if you'd taken a single GMPE and you looked at its standard deviation, let's say as a function of magnitude, would that have fallen inside of the, in other words, are the gray lines in some ways also meant to say, well, here's the randomization if you had all these medians, that your GMPE should have in fact been within inside of that?
Can you go back to your part with just the gray curves? And I think part of what helps, Ralph, in looking at one of those, that range is actually really similar to our validation range that we gave you.
Right.
I looked, which was not intentional, but we had about a factor of 3, which would be a 1 on here from the low to the high from what was allowable, and we're creating essentially that kind of a range here. So this is ranges and medians. It's not intended to be the aleatory variability part. So you could have a median as high as near the top of that or as low as near the bottom. What Doug was saying is some of these probably are actually too far out and we need to reject, like the ones where they're bending back up again, right? That's part of the consequence of generating them only to 30 kilometers. But the range seems reasonable to me just from looking at what we had tried to get at for what's allowable from the simulation range, and what we can say is our ability to constrain empirically the GMPE. Thank you.
Just if you put the magnitude scaling one, since you're right here, Doug. also looks like some of those extreme values on the low end are oversaturating as well, which you need to evaluate on whether you want to allow that or not.
We've been talking about that in the last few days, is what we're doing here, and we're going to need to look at eliminating some of these models. So we'll generate 1,000, but they're correlated parameters without a lot of constraints on them, and we need to come back and say, is this violating something that the developers would not have created themselves?
So, Norm, it means that after, say, Nico is done, these will be reviewed by human beings?
Yeah, we need to review them before they're taken. Yeah.
Just to make sure that there is a sanity check that, as you just said. Okay, yeah. Very good.
Let me add to the big picture here. The fundamental issue is that we have GMPEs published, and they're point estimates of what could be the space of models. And we're limited by what happened to make it through the publication process and so forth. Those models are descriptions of data, but they also have a lot of other interpretation that was built into them. Many of you have heard me say this before. The art of the GMPE is not data fitting. It's how it extrapolates to where you don't have data and where you're going to use it. That's really the whole key. So we're trying to build models that would also extrapolate in a reasonable way by looking at the correlation structure. But fundamentally, we're trying to expand that space of 6 or 10 representative models and say, you know what, there could have been other ones, not just in between, but a little further outside to capture the range of models that might be coming up in the next 10 years, not just what happens to be available today. So epistemic uncertainty needs to track what could happen as well as what's been published. It's not limited to just the available ones. This is really giving us a structure to start to do that in an organized way. And we've been at this for years, and I'm really happy that Nico's been here the last 6 months to get this to the point where I think we can implement. By the time we're done here, if you stay around for 3 days, you're going to understand this stuff, okay? It's going to make sense to you, because I think it takes several times of seeing it and hearing it.
Steve. This is characterizing epistemic uncertainty. Will this replace the earlier efforts to add near source epistemic uncertainty, or does this subsume that effort, or will that be added in addition?
So
I'm sorry, it's very hard to get this thing close enough.
Maybe turn it this way. Or
yeah. I was asking whether this analysis of epistemic uncertainty would completely replace or subsume earlier efforts in the project to characterize near source epistemic uncertainty.
The concept is, yes, it would replace it, but we need to make sure that it does, right? So we get this range here, near source. Is this mimicking that behavior? Okay, so if it doesn't have as big a range as what's coming out of the statistical uncertainty that Bob and Linda put together, then they'd have to be broadened. And we could do that by broadening the models in the first place before putting them into the correlation structure. But right now, our idea is that it will just come out of these, because this is also showing you the range of what the models could be. That's a test for us to demonstrate to you that this captures that same range. Nico, have you looked at it?
Other side.
At very short distances, it maybe doesn't capture everything.
Yeah. So we may have to broaden it out.
The main reason is that at short distances, the DSSA model is the highest one, and we're not capturing that well because we're using rupture distance and not China wood.
Doug showed that DSSA is a good example because they use RJB, others they use RRUP. But Doug showed that you can have it after another separate entity. I think that's very good, because so if there is a GMP with a specific uniqueness, are strange, we are excluding. That's a good thing. And definitely, this is much, much better than backbone curve, one GMP scaling up and down. That's 19th century approach.
One of the interesting things is that when you look at GMPEs that weren't used to construct the correlation structure and it's resampled, that those GMPEs that were excluded in that process are falling within the distribution, that they're not outside of that.
Any other questions? Again, you'll have several more chances, so we're just making sure you have the idea of where we're going. So when Nico starts out, you'll be able to hang on and get through it all.